Oh wait, that part's good. No, it's not. I need to set the source over here for the presentation part this way, and mess with okay, and again.
Whatever you just did made the screen big.
It made it bigger?
Yes, it's made it almost perfect.
Wow. Let's go with perfect. It made it perfect.
Okay, it's made it perfect.
Okay, so that's interesting. It's just, it may have something to do with the projector. Okay.
Right.
So, great. We got all this stuff going. And so, any questions right now on anything? Stuff beginning with chapter 4, anything there? No? Okay. How many do I, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Let's see, one person. That makes 12. I know where somebody else is. That makes 13. And so, okay. Got it. All right. So, we are in this thing, chapter 4, which is anti-differentiation and integration and all that sort of stuff. The one thing that I think is, the jury's out from my perspective on, is whether the way many books introduce this idea of integration is really the best thing to do. It's a very intuitive thing. So they introduce through area, and we talk about area under the curve. But I think what happens a lot when you get introduced to integrals as area under the curve, you begin to believe sort of that's the definition, and it's not at all. That's merely an interpretation of the mathematics, and it's a very nice interpretation of the mathematics. It's a very good representation of what's going on, okay? But it is by no means the definition, and so I think you end up sort of losing some of what you can do, or sort of the real power of it, because I think what happens is many people just attach that area under the curve thing, and unless they're asked about area under the curve, they don't necessarily see that an integral is applicable. Okay, so what I'd like to do, we've got a bunch of videos introducing the various sections so far. What I'd like to actually do is jump ahead to something. Now, you don't see this particular problem in chapter 7, but I want to jump ahead to something like what we would see worded in chapter 7. And so you may have, a liquid is flowing at maybe 2 liters per second. Okay, so you've just got this flow of 2 liters per second. It's coming out of the tap or something like that. And, a question that hopefully we know how to answer, how much liquid is accumulated in 10 seconds. Okay, now actually that question would not be asked in Chapter 7. Well, it might be in the discussion of Chapter 7 or something like that. But, well, I've got my flow rate, 2 liters per second for 10 seconds. Hey, we're science type people. We get the idea of units and all that. So my accumulation or my total volume, V, is just going to be that 2 liters per second times my 10 seconds, right? Units, dimensionality works out there, units cancel out, and I get 20 liters. That problem is easy. We can do that problem, piece of cake. Now, though, where does calculus come in? Well, we get a new question. Like we have liquid is flowing at 5 minus 1/2 t liters per second, where t is seconds. Okay, so we have something like that. The flow is changing. Okay, it starts out at 0 seconds when I guess when I first turn it on, it's flowing at 5 liters per second. But now if I ask, how much liquid is accumulated, so how much liquid is accumulated, in 10 seconds, not so obvious. Okay, and I'm using liquid. I think we can relate to that a little better than, I could have used an electrical charge, because actually that's how capacitors work, is that capacitors charge up to a certain amount, and then like if you turn off the electricity, that capacitor is charged, it will discharge at some rate, so it would lose its thing. That's part of the reason why a lot of your electronics equipment says unplug, and they'll even sometimes say things like ground or something before you mess with it. And the reason is that you might start messing with something that has a capacitor in it, and that capacitor isn't dissipated yet, so it's carrying a charge. And you might hit something, and not that you would necessarily get hurt, but that you might hurt the equipment because all of a sudden you allow a path from this capacitor to something else that it shouldn't get. So, something like that could be happening, right? Is that the liquid, maybe I have a bucket of liquid or something, and I open up a spout, and it starts flowing out real fast, but as the liquid drains out, it flows slower until there's no liquid. Okay, so maybe we have something like that. Well, now it is definitely not so obvious how much liquid we accumulated. Okay, but what we can do is we can use this model in little pieces to approximate what's going on there. And so it's going to be 10 seconds. What I could do is ask, well, okay, how about, let's see, 1 second. Okay, in 1 second, what I could do, I could get a reasonable estimate, because during that 1 second, flow started at 5 liters per second and dropped to 4.5 liters per second. Those are pretty close numbers, right? They're pretty similar numbers. So I could probably just say, you know, over that second, it was flowing at like 5 liters per second. Or, I could go with 4.5 liters per second. Probably either one of those would be fine. And actually, if we kind of follow the book's ideas, is we could bound it, right? Well, there could be no more than 5 liters and no less than 4.5 liters. Does that make sense? Right? The most in that first second I could possibly have would be 5 liters, and the least would be 4.5 liters. Okay, because I can just look at this function and see that it's decreasing, and so it's biggest when t is 0 and smallest then when t is 1 at 4.5. Okay, so I can get the change in the first second. So what I could do is I could say, oh, my delta V, my change in the volume during that first second, is equal to, well, I'm just going to take that flow rate there and, well, I should actually say approximately equal to. And again, I could go with an upper bound or a lower bound. You know, it's approximately equal to, I like the 5 just here, so 5 liters per second times 1 second, which is 5 liters. Okay. Any questions on that at all? It's just an estimate, but I'm using the information I have. I know the flow rate, somewhere around 5 liters per second. I know that I'm doing it for 1 second, and I realize it's changing, right? So it's approximately that. Okay, and I could have used 4.5. And we could actually bound it, you know, so more precisely, in this particular case, I know that 4.5 liters is less than or equal to the change in volume over that first second, which is less than or equal to 5 liters. Okay. Anything on that? I mean, I would like to think, you know, it's just obvious that that's true, and so, you know, but well, it's not always. So, okay. So that was the first second, and then I can do the same thing the second second. Okay, so second, how about that? Call that change in V2, my change in volume. And that, actually I should move it over a little bit so I can put it between these two things. All right, so my change in volume here, I can do the same sort of thing. I erase my 5 minus 1/2 t, right? But in this second, I'm between 1 second and 2 seconds. Okay, I'm between 1 second and 2 seconds. So at 1 second, this was, we already know that answer, that was 4.5 liters. But at 2 seconds, it's the 5 minus 1/2 times 2 liters per second times 1 second liters. Okay, so 4. So this one's 4 liters. V2 is between those two. Any questions on that? That during that second, okay, because I'm going from 1 second to 2 seconds. At 1 second, it's draining this, well, this, because we're multiplying by a second, that number, that magnitude is both the rate and the volume. But it's going out at 4.5 liters per second. And so that's the most it could be draining at. And the least it could be draining at is 4. Okay, and so then I could go down, and I'm kind of seeing the pattern here. I could have change it in the 3rd second. Well, that's going to be less than or equal to the 4 there, and drop by a half a liter per second at the end of the 3rd second, and so that's going to be 3.5 liters. 4th second, that's going to be less than 3.5 liters and greater than 3 liters. Okay, and everybody's with me on this? That's how much how much has drained. Again, I don't know exactly, but I know it's between those numbers. Okay, up to 5 seconds here. 2.5 liters and 3 liters. Okay, and then, so I'm going to have 6 seconds, 7 seconds, 8 seconds, 9 seconds, and finally 10 seconds. So if I did this right, this will be between 0 and a half a liter, if I did it right. So hopefully I did. So let's get those. And as I say, you know, at this point I'm kind of just looking at the pattern and seeing it's going down by a half. So this is 2 liters, 1.5 liters, 1.0 liters, 0.5 liters, and 0 liters. Awesome. That's what I was supposed to have. And this one was 2.5 liters, 2 liters, 1.5 liters, 1 liter, and 0.5 liters. So now I've got an estimate of this change each time. And what I'm doing is I'm taking, I guess I'll call it a physics formula. Okay, it's kind of like distance equals rate times time, but here it's a rate times time, but it's not a distance, it's a volume. So our volume is equal to rate times time in this case. Okay, so I've got all those. And now, the sum total of my accumulation, the total change in the volume, is just the sum of those 10 volumes. Okay, so I'm going to go ahead and erase this volume here that started out with the 4.5 and the 5. But so I need to take those, and I'm getting really tired of writing that, but one of the first things the textbook does is point out this thing called summation notation or sigma notation. And so I want to add up V1, well, delta V1 through delta V10, and so I use an uppercase sigma, Greek letter sigma, to say I'm going to do a sum. It just means whatever you see there, make them all, and then just put plus signs in between them. And so what are all of them? Well, I equals 1 to 10. Okay, so it's my subscript here. And it's my delta VI is what I want to add up. So it's just so much better than writing V1 plus V2 plus V3, well, and with the delta part, right? And writing all that, and then maybe a dot, 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 and, you know, it's just a way better notation, much simpler. And so that is going to be my total change in V, right? So that's my total change in V. And so from that, what I can see is that V is, my total change in V is between, well, I add up all the left side. So that started at 5, or no, sorry, 4.5, and went down to 0. And the other side started at 1/2, and well, actually, I guess started at 5 and went down to 1/2. Okay, so, well, I've got to add those up. If I was, you know, a little more clear-headed right now, I could probably add it up very, very fast. But here, I've got 1.5, 3, 5. So I'll just add it the old-fashioned way. So there's 5. That one makes 8. And there are 6 more there, so that's 14, 18, 22.5. Okay, so I get 22.5 liters here. And on the other side, well, for all 10 of these, I had a 1/2 liter more. Okay, every single one of them I had a 1/2 liter more, so that's 5 extra liters. So I assume, I think, that we should get 27.5 liters for the other side. Okay, so I don't know the answer, but I have an estimate. Okay, and I think the important thing here to really get is, you know, what did I do? Well, I didn't know how to do the problem from start to finish, right? And in a way, I still don't, because I only have it bounded between things. But I didn't know how to do the problem. But if I made it small enough, the difference from beginning to end of that time interval really wasn't very much. And so I probably didn't have much error. Okay? And how could I do it better? Well, it seems reasonable that maybe if I made, instead of doing a second, if I did every 1/10 of a second, that might do better. Okay? I could do every 1/10 of a second. Now, why might that do better? Well, because if I go every 1/10 of a second, then the difference, for instance, at the beginning is only 0.1, right? It's 5 liters per second. Or actually, 1/10 of a second, I guess it'd be 0.05. So it'd be then 4.95 liters per second. Okay, so if I make the interval much smaller, my estimation is probably much better. Now, I think a question that could come up is, well, yeah, but I've got more intervals that I'm estimating over, so, you know, if you really think about it, it's not clear that that will give you a better estimate. It seems reasonable that it should. Okay? Now, if I do that, right, now I'm not going to go through that whole thing, but I could get, you know, a delta V1, a first one. Now in that case it's not going to be 1 second, but, you know, I know if I go for just a 1/10 of a second, so that's 5 liters per second times a 1/10 of a second, that would be 0.5 liters. Okay, if I change to my delta T is 0.1 seconds now. Then on this side, well, okay, I had 5 minus 1/2 T, and so T would be 0.1, and that's 0.5 times 0.1, that's 0.05, well, and then times 0.1. This becomes 4.95, and so this is 0.495 is less than or equal to delta V1 less than or equal to 0.5 liters. And so now you see the difference. My error here went from 1/2 liter, okay, the width of how much I didn't know, right, went from 1/2 liter down to 0.005 liters. Did I do that right? I think I did. Yeah, I think I got that right. Right? Oops. Well, I need to put the 0.1 in there. So, yeah, that's 0.05. Yeah, 495. Yeah. And so, much smaller error. And actually, each one of these is going to be that same way, right? So here, my plus or minus error, my total width of my interval, looks like it's going to be 0.005 each time. And if I do this for 10 seconds, right? I'm doing this for 10 seconds, so I have 100 of these. Does that make sense? I've got to do this 100 times. Well, so if this is the error, the error between each of them each time, and I do it 100 times, my difference in the two volumes is going to be that much. Okay, so I'm going to drop from 5 difference to 0.5 different. So it does work, right? So I get a better answer. My error is much smaller. It's 10 times smaller. Okay, by dropping the time by a factor of 10, I reduced my error by a factor of 10. That's nice. So if I went to 100th of a second, I guess I could get them within 0.005. Okay, so this method appears to work to get an accumulation. Okay, so this is what we want to do, and doing this sort of thing is called an integral. And notice that what we set up here was this summation, but it was a summation of a very certain form. Okay, so I have this sum from I equals 1 to whatever n I'm choosing, and it was all a bunch of small changes. Okay, but more importantly, the way those changes were made was that I took my function, my flow rate function. So it's the rate of change of the volume, right? It's the rate of change of the volume, so I could call it V prime. And so I was taking V prime at some t value, T sub I, and multiplying it by some small change in t. That's what I did. Okay, questions on that? See, so I jumped to this derivative, but remember, it was flow rate. It was the rate of change of the volume. And so if it's the rate of change of the volume, it's V prime. Rate of change, derivative, right? So I did this, and it looks like, you know, from kind of thinking about these errors and adding them all up and so forth, it looks like as I let this delta t go to 0, make it smaller and smaller, this error is going to go to 0, and I'm going to get an answer. Okay, and by doing that, this process, when we say, okay, let's let, and you could say n goes to infinity, or you could say, in this case, delta t goes to 0. They're really one and the same, right? As I make delta t go to 0, I've got more and more and more of these intervals. As I make more and more intervals, delta t has to get smaller and smaller. The sum 1 to n ti. For this, when you and in this case, to 10, actual limits of what we were interested in, 10 seconds. So 0 to 10 of v prime of t dt. And we go from a delta t to a dt. Now, actually, technically speaking, they're one and the same. Okay, when you see something like that, we call it a differential. And actually, what's happening back here with these delta v's is that we're saying, because what we actually did was we did that. We're saying that the real change in delta v at some location in there as I do it is approximately the same as what we call dv sub I. And I mentioned this in a video. This is a kind of a subtlety. Here I have the dependent variable. And so when I talk about a delta or a change in the dependent variable, the function value, I'm saying that's approximately the same as this thing called the differential. However, here, v prime at ti and then dt, here, dt and delta t are synonyms. Synonyms, yeah. Okay, they're synonyms. They're the same darn thing. They're each a positive quantity. Some number greater than or equal to 0. So these are equal to each other. They're the independent variable. So it's just one of these subtle language things, you know, that if I'm talking about this dt here, then that or a delta t doesn't matter. You know, so here, actually, I could have been writing dt the whole time. So to go from a delta t here to a dt there, not really a big deal. Now, actually, and this is, to me, one place where this whole idea of limit-based stuff in calculus is actually a slight problem intuitively. There's also calculus, Newton's calculus. So if you go back to Isaac Newton, well, actually, I think Leibniz as well. So they were contemporaries that each invented calculus. And so, of course, the Germans and the Brits, you know, fight over who truly invented it. You know, so, but the best anybody can tell, at least as far as I know from reading the history stuff, they truly did it independently. But they both used sort of this idea called an infinitesimal. And the notion of an infinitesimal is a really, really small amount that you can't really measure it. And if you start talking infinitesimals, then, you know, here, when we do this, right, this is equal, but it's only approximately equal to the change. But if you say, well, actually what we're talking about here with this dt is an infinitesimal amount. What the heck is that? It's really small. Well, what does that mean? Well, it's so small that actually these two things at that point are equal. Oh, okay, right. But you know, for me, I kind of learned that. I was taught that when I learned calculus, and oddly enough, that kind of made sense. Is that if I look at this, you know, this is an approximation for big stuff. But when we start thinking about the limit and going to really, really tiny stuff, oh yeah, you know, these are one and the same. If I see a dv or a delta v, and I know I'm talking about really, really, really tiny, tiny amounts, then they're one and the same. It's only when they get bigger, right? When this delta t or dt gets bigger that they're not the same. Okay, but this is this idea of a definite integral, and you see, you can come about this notion without ever talking about area under the curve. Okay, it has a great deal to do with area under the curve if you look at it that way, but it doesn't have to. Okay, what it really is, when I see this, I think about adding up a bunch of little things like that. Okay, that's what it's doing. Now, a great way to interpret that graphically is with area under the curve, because now, you know, again, we aren't talking about area at all, right? This isn't area, this is volume, which I guess is kind of related to area. But again, I could do it with electric charge. You know, I could have said this was a capacitor, but then everybody would have done that. Huh? What? You know, maybe not everybody, but right. But some of you, what the heck's a capacitor? But you know, when you think about volume and flow rates, you know, we've all seen water coming out of a tap, pouring out of a jug, going down a river. We've seen that stuff. So, so here we were looking at volume, but if I draw a graph of this. There's T, and here is our flow rate, so I'm going to call it V prime of T. And it would look something like that. Okay, there's 5, there's 10, and this is 5 minus 1/2 T, like that. Then when we broke this up into 10 pieces, a graphical representation of that is, okay, here's my first second right in there from 0 to 1. And when I took the 5, you know, I plugged in 0, and I said, okay, I want 5 times 1. Well, that is the same as the area of that rectangle. So that is a great representation. Okay? But again, that area is just that. It's just a representation of my multiplication of 5 times 1. And that's all it is. It's just a representation. But it's a great one because I can think of that as area, and if I'm thinking of it as area, I really wanted this area down here, but I got that little bit of extra, it was too big. And on the other hand, you know, if I'm looking at this one, the second, when I took the lower bound, I was thinking about that area. Okay, again, well, I was thinking about taking, and that would be at 4. So I was thinking about taking 4 liters per second times 1 second, but that's exactly the same number as I get for that area. So I could think of taking that 4 in the second as an underrepresentation. Oh, but I can actually see that here too, is that I really wanted all of this, but I only took that much, and so this thing up here was how much I was short. Okay, I was short by that much. Now, in this particular case, notice what happens though, is the amount I'm over by is exactly the same as the amount I'm under by. Because there are 2 triangles that are the same size. Right? And so actually, I erased it. What did I have, like 22.5 and 27.5? So if I take the average of those two, which is 25, that is the answer in that case. Okay, and I can see it geometrically. And that's the other thing is, oh, now that I've got this representation, I could use this area to give me my answer. Okay, so I look at that area, and that area, well, that's a width of 10, a height of 5, it's a triangle, 1/2 times 10 times 5, 25. So I could use this interpretation of area here to actually evaluate this limit. Okay, and again, you know, let's take a much smaller spot here. So when I shrunk this down to 1/10 the size, right, when I make those triangles, those errors are indeed much smaller. And if I put that inside a bigger rectangle like that, and then I keep making those, well, I can see that, you know, I'll fill in a bunch of error triangles like this. Oh, so I'll get rid of all that error if I go to smaller rectangles. Okay, and again, so I'm using this interpretation, this representation of area, to help me gain insight as to what I saw happen. Okay, but what I saw happen could happen regardless of whether I could have drawn it or not. Right? It was all about the numbers. Okay, and adding up those changes. And so what we're doing with something like this is that, you know, I have a function, and I would like to know if I go this far, how much is that, right? So there's my delta f, my change in f. But what I have available as far as information is not the function itself, but its rate of change. And so what we were doing here is we were taking that rate of change and coming up with this, which would be our df. We were taking the slope of that line times that either delta t or x or whatever, or dx. And I was multiplying that length there times the slope, and well, right, I've got a straight line, so df over either dt or delta t is the slope. Oh, well, so multiply the slope by that delta t or dt, and I get df. Okay, and that's what we were doing. And so that's what these definite integrals are, is just a way to use the rate of change to determine a total change in a function. So given the function's rate of change, can I recoup the function's total change? And I can. And I can do it through this thing called a definite integral. Okay, and it's amazing, really, I think, that then with the fundamental theorem of calculus, we were doing definite integrals as a race, or the human race, and derivatives, but we didn't know they were related. And so then we've got this fundamental theorem of calculus, right, that says, hey, actually, if I've defined this integral here, this definite integral, I can actually evaluate it. So here I've got f prime. So here's the antiderivative, like that. And there is our fundamental theorem of calculus. It says, hey, if I got this function and I know it's antiderivative, I can tell you the change in that antiderivative simply with a definite integral, or the more important part is if I want to add up all these things, as long as I know the antiderivative, I can just do it this way. And so for our problem, what we wanted to do was the integral from 0 to 10 of 5 minus 1/2 t dt. And that antiderivative is just 5t minus t squared over 4, right? Because I make the 2 divide by 2, so I'll get t squared over 4. And I evaluate that at 0 and at 10. Well, at 10, I get 50 minus 100 over 4. And then minus, so there I've evaluated the upper one. Now minus, well, and I just get 0 minus 0. And so that's 50 minus 25. I get that 25. It's magic, right? This fundamental theorem of calculus with derivatives and antiderivatives, quite magical. And so that's what this stuff's doing, okay? Is as you go through, your kind of drill stuff with just doing antiderivatives and filling them in, that kind of thing, realize that what you're doing is you're taking that original function, like this one, that rate of change, and you're adding up a bunch of things that look like that. Okay, you're taking the function times a little piece to kind of gather up that change, and that's what's happening. Now, it's pretty hidden here. I just need to know my antiderivatives. But that is what we're doing when we see this kind of notation. All righty. Well, definitely to the end. And I will see you on, what's today, Monday? Thursday.